Good afternoon, everyone. I am basically an organic chemist. There's a lot of organic synthesis and characterization by spectroscopy is main objective of the work. So, a thorough knowledge of spectroscopic techniques is essential if you want to be successful in doing organic synthesis. Among the spectroscopic techniques, NMR is highly useful for organic chemistry research. And we have a course in spectroscopy wherein the NMR is discussed in detail. That course content is available in the NPTEL. I have offered one course in spectroscopy. It is freely available for everyone. If you type in Google spectroscopy Sankararaman, you probably get it. What I am going to talk in this lecture is the use of NMR spectroscopy to study dynamic processes in the chemical systems. NMR spectroscopy basically, if you have ethyl alcohol, there are three different types of hydrogen: CH3 hydrogen, CH2 hydrogen, OH hydrogen. So essentially, it will give you three signals in the NMR spectrum. The fine details of the spectrum, of course, depends on the coupling between CH3 and CH2 and so on. So the ability of NMR is to distinguish among hydrogens in the molecule. If there are 20 hydrogens and all of them are chemically non-equivalent hydrogen, chemically non-equivalent essentially means that it is not under identical chemical environment. The electron density around each of the hydrogen is different. This is what it means. NMR will definitely distinguish and show 20 different signals, provided there is no overlapping of signals in the NMR spectrum. If for any reason a molecule is undergoing a process wherein hydrogen positions are exchanged, for example, the OH hydrogen, if you take, the OH hydrogen doesn't stay in one oxygen all the time, it hops around from one oxygen to another oxygen and so on. How do we know this? If you look at the NMR spectrum, the OH peak will be a broad peak and it is generally exchangeable to deuterium and so on and so forth. Some of the dynamic properties of the molecules is listed here. Conformational changes. We have studied in stereochemistry. Cyclohexane has a conformation which is chair conformation. And the chair to chair interconversion is a dynamic process that we talk about in cyclohexane. Restricted rotation around carbon-carbon bond and carbon-nitrogen, carbon-oxygen, carbon-sulfur bonds. If you take something like N-dimethyl formamide, the nitrogen lone pair is delocalized onto the carbonyl oxygen. That makes the carbon-nitrogen bond as a double bond character. As a consequence of the double bond character, the bond doesn't rotate freely, it has a restricted rotation. Such a restricted rotation can be easily studied by NMR spectroscopy. As I go through the examples of various types of processes, if you have any question, you stop me by putting your hand up. and raise your questions and queries. I'll be happy to answer and then proceed. I don't want you to leave the room with a lot of doubts in mind. And one of the things that you find in IIT Madras classroom is generally the classroom is quiet, students don't ask any questions. But after the lecture is over and this teacher is in this room, they feel free to walk into your room and ask questions about the lecture. This has been my experience with students. I encourage that with the students. But in your case, you don't have to come all the way to my office. You can just ask questions. The NMR tube, which is a 5 millimeter tube, about 1 centimeter long tube, it can be cooled to minus 150 degrees centigrade using liquid nitrogen. It can also be heated to plus 150 degrees Celsius. So you have a window of about 300 degrees to manipulate the dynamic processes. If a chair conformation is going from one chair to another chair, it will be dependent on the temperature of the reaction condition. Under very low temperature, one can freeze the interconversion of one chair to another chair, for example. So the variable temperature technique is a very valuable technique in the NMR spectroscopy. With this kind of a temperature range, one can study activation barriers typically in the range of 8 to 25 kilocalories per mole. In other words, the process takes place with an activation energy. The activation energy, if it is within the range of 8 to 25, one can study this by NMR variable temperature. Let's assume there are two types of protons in a molecule. Typical example would be the axial and the equatorial hydrogen present in the cyclohexane. They have distinct chemical environment, so the axial hydrogen and the equatorial hydrogen should come separately in the NMR spectrum. The ability of NMR to distinguish between the two protons will depend upon how long the protons spend time in the axial position and in the equatorial position. Suppose if the axial proton remains in the axial position and the equatorial proton remains in the equatorial position for a prolonged period of time, NMR will clearly see the axial hydrogen and the equatorial hydrogen and give two separate signals. On the other hand, in the other end of the spectrum, if the interconversion between the axial and the equatorial proton is very high, NMR will not see the axial hydrogen sitting in the axial position long enough to record the signal. Under those conditions, both the signal will merge and it will give a single peak for both axial and the equatorial hydrogen. The energy difference between the two states is as small as 10 to the power minus 7 calories per mole. Therefore, the lifetime in any particular state should be sufficient for NMR to give the correct chemical shift value. The axial position and the equatorial position exchange process can be rapid process, in which case NMR will not distinguish the two, or it can be a very slow process where the NMR can distinguish the two. There is a situation where the axial proton doesn't sit in the axial position long enough, but at the same time, NMR is not able to distinguish between the two positions. This is because of uncertainty principle operating in certain temperature range. Under certain rates, there is an uncertainty with respect to the NMR time scale, whether the axial position proton is sitting in the axial position or not. Such an uncertainty principle is expressed in terms of the lifetime and the energy difference between the two positions of the protons. This is very clearly manifested in the NMR spectrum at various temperatures. This is essentially what I said now. If the proton is exchanging between two states very rapidly, then NMR will give only an average signal. Proton exchanges between the two states slowly, then NMR will give individual chemical shift states. The rate of such chemical processes can be controlled by temperature as well as concentration. So you have two tools in your hand. One is to vary the temperature, other one is to vary the concentration of the solution. Let us look into some examples of dynamic studies due to conformational changes. Here the experiment is done with cyclohexane D11. In other words, in all of these positions, hydrogen is replaced by deuterium. You have only one hydrogen present in the system. So if it undergoes the chair-to-chair conversion, the axial position is converted into an equatorial position in the cyclohexane system. Just having only one proton is convenient to study. That is why they have made the cyclohexane D11 and made the study so that deuterium does not interfere with your other hydrogens. If it is present, it is going to give a complex spectrum. So in order to avoid the complexity of the spectrum, just to have only one proton that will show up either in the axial position or in the equatorial position. The spectrum recorded shown here at minus 89 degrees centigrade. There are two peaks that are seen here, and the peaks are assigned to equatorial hydrogen and axial hydrogen. So under these conditions, at the low temperature, the exchange process is not taking place rapidly. We heat the sample and go to minus 49 degrees centigrade. Obviously, the two peaks are merged at some point between minus 60 and minus 63 degrees centigrade. And this is known as the coalescence temperature. Somewhere around 62 degrees or so is the coalescence temperature. Coalescence temperature is the temperature at which the two states sort of merge to give a single state. And if you still heat further to room temperature, it will give only one signal, sharp signal, the axial and the equatorial hydrogen. Here is an example where carbon-13 spectroscopy is used to study the dynamic process of 1,2-dimethyl cyclohexane. 1,2-dimethyl cyclohexane, the chair-to-chair interconversion takes place. The axial hydrogen becomes equatorial hydrogen, axial methyl becomes equatorial methyl, and equatorial methyl becomes axial methyl. If I put a mirror plane across here, you can see that this is a mirror image of this system. These two are mirror images, and hence they are enantiomer in nature. 1,2-dimethyl cyclohexane is a chiral compound. It exists as a pair of enantiomers. The enantiomers are interconvertible when simply doing chair-to-chair. So it is an example of a non-resolvable enantiomer mixture, racemic mixture. Suppose if it is rapidly undergoing interconversion between these two states, NMR will see an average state which is going to look like this. In this particular state, there is a plane of symmetry, and the plane of symmetry essentially makes the molecule look like it's a non-chiral, achiral compound. So the NMR will sorry about that. NMR will see this as a transition state between these two structures. So if you take this structure alone, at low temperature when the interconversion is very small, the interconversion is very slow, how many signals you will see for this depends on the number of different types of carbon present in the system. Clearly, the 6 carbons present in the ring is entirely different from each other. And the 2 methyl groups, one is axial, the other one is equatorial, and that is also different with respect to each other. So 6 carbons plus the 2 methyl carbons, totally 8 carbons are expected for this compound. Take a look at the NMR spectrum at 223 Kelvin. Low temperature, you see 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons can be clearly seen. 2 carbons are overlapping here and 2 carbons are overlapping here. Other than that, it is a clean spectrum in terms of identifying the 8 carbons in the molecule. So NMR is able to see the frozen structure, so to say, at low temperature. Because of the chiral nature of the structure, all the 6 carbons of the ring are different and the 2 carbons of the methyl are also different. 8 carbons are seen in the spectrum. At high temperature, when the interconversion is very high, NMR is going to see an average structure, which is this structure. How many peaks do you think we'll get in this particular case? 4. Because of the plane of symmetry, the upper half is identical to the lower half. So it is 1, 2, 3, 4. 4 signals are seen. So you can see 4 signals in the NMR spectrum of the compound. Such a detailed study gives you a handle in calculating the activation barrier for this process. Activation barrier is usually calculated using Eyring equation. particular temperature, namely the coalescence temperature. Activation barrier can be calculated. The rate can be calculated at the coalescence temperature. Kc corresponds to the rate at the coalescence temperature, which is delta nu is the difference between the chemical shift value of the axial and the equatorial hydrogen in the case of cyclohexane. Now let us take the example of X is equal to sulfur, which is trithiene molecule. Trithiene molecule, okay, the dynamic process is chair interconversion. This particular case, the three axial hydrogens and the three equatorial hydrogens are equivalent because of see-through axis of symmetry in the molecule. There is a C3 axis of symmetry which you can see the center of the molecule going through like this. That makes the CH hydrogens in this position equivalent to the CH hydrogen in this position. Under slow exchange conditions, remember the axial hydrogen and the equatorial hydrogens are chemically non-identical, chemically non-equivalent in nature. So they will couple with each other. Coupling will, A will spin couple with B to give a doublet. B will spin couple with A to give another doublet. So you see what is known as the AB quartet. Under very fast exchange, there is no distinction between axial and the equatorial hydrogen. So fast exchange will give a singlet for both the hydrogens of the molecule. Activation barrier has been calculated to be about 10.9 kilocalories per mole in this particular case. Are you following me until now? If you have any question, please raise your hand. Here is another example of tetra-deuterosubstituted piperidine, nitrogen analog of this compound. The deuterium substitution is it going back. Here, these two hydrogens in this position and these two hydrogen in this position are equivalent because of this plane of symmetry of the molecule. Whereas these two hydrogens are distinctly different from the four hydrogens in the two position. So at low temperatures, it should give essentially an AB quartet for the hydrogen in the 2 and 6 position, and then AB quartet for these two hydrogens in the 4 position. So it should be giving 2 AB quartets. What you see in the spectrum is the AB quartet here, corresponding to the 2 position and the 6 position, and another AB quartet which is at a higher delta value. As you increase the temperature, go to minus 50, minus 40, the AB quartets collapse to a singlet, and you essentially get 2 singlets, one for the 4 position hydrogen, the other one for the 2 and 6 position hydrogen. If you integrate and take the area under these curves, it will be 2:1 ratio. And there is a 2 position, 6 position, 4 hydrogens versus 2 hydrogens, 1:2 ratio. These are some examples of carbon-carbon bond rotation, carbon-nitrogen bond rotation, carbon-chlorine bond rotation, and so on. Tertiary butyl cyclopentane, if you take, and if you view the molecule along the carbon-carbon bond, along this carbon-carbon bond, what you will see is essentially a stable conformation, which is this conformation here. This conformation, these two methyls are identical, and this methyl is different from the other two methyls. In other words, one methyl comes just below the cyclopentane ring, the other two comes away from the cyclopentane ring. So at 150 degrees centigrade, two singlets of the resonance 2:1 ratio will be obtained. In this particular case, these are the stable conformers of this molecule. So the rotation around the carbon-carbon bond is sort of hindered because of the chlorine, which is a bulky substituent. There are 4 chlorines in this molecule, and in this case, the two methyl groups are chemically equivalent because of the C2 axis of symmetry which is passing through this molecule. In this molecule, there is a plane of symmetry, C2 axis of symmetry along the plane here. So at low temperature, when you measure the spectrum, it gives two singlets because of the fact that two methyls are equivalent, they are giving a singlet. These two methyls are also equivalent, they give a singlet. As a result of that, you see it's two singlets in the ratio 2:1 ratio, 2:1 corresponding to this being 2 times more concentration compared to this one. The equilibrium is such that in the equilibrium, the ratio of the two conformers is shown as 2:1. One can use fluorine NMR instead of carbon and hydrogen NMR. Fluorine 19 is a NMR active nucleus, and it is 100% abundant nucleus. This molecule is known as tryptosine. It is a propeller-shaped molecule. If you look around the carbon-carbon bond axis, what you will see is a benzene ring. This is a benzene ring. This is how the molecule will look like. It's a cartoonic representation of the molecule along the carbon-carbon bond view. There are two processes which are dynamic in nature in this particular system. One is a carbon-nitrogen bond rotation. Here you will have restricted rotation because of the fact it's a highly sterically hindered position because of these 3 hydrogens. Steric hindrance is what is causing the restricted rotation in this particular molecule. In addition to that, there is also pyramidal inversion of the nitrogen. Ammonia, for example, can pyramidally invert itself to another form of ammonia, which is mirror image of the original form. Such a pyramidal inversion is possible in this vein also. If you take this molecule here, the nitrogen atom is a chiral nitrogen atom because there are 4 different substituents on the nitrogen. It corresponds to chirality of nitrogen. That makes the CH2 as a diastereotopic hydrogen. You know the difference between enantiotopic hydrogen and diastereotopic hydrogen. Enantiotopic hydrogens are related by a mirror plane. Diastereotopic hydrogens are not related by mirror plane or axis of symmetry. That is the case. It will give a AB quartet for the CH2 functional group. AB quartet is seen at low temperature where the rotation of the carbon-nitrogen bond is slow. As you go to higher temperatures, the rotation becomes fast and the NMR is no longer distinguishing the two CH2 hydrogens. So it appears as a singlet in this spectrum. Take 2 minutes more. I have to skip many of these slides, otherwise it will go on and on. This is interesting case. The diamagnetic ring current effect will shield the hydrogen which are interior of the aniline system. So these 6 hydrogens will be highly shielded and this 12 hydrogens will be highly de-shielded in nature. Low temperature, this is a highly shielded hydrogen -3 delta. This is 9.6 delta or so, which is highly positive de-shielded hydrogen. At high temperature where the large ring system can undergo dynamic process of rotating this hydrogen, bring the outside hydrogen inside and the inside hydrogen goes outside. That is the case. NMR will not be able to see this hydrogen either inside or outside. There will be uncertainty. Under high temperatures, where the interconversion is very high, the interior hydrogen and the exterior hydrogen appear as a singlet together. Plus 40 degrees, if you look at the spectrum, it is essentially baseline is what you are seeing. Uncertainty is so high here, NMR doesn't see the 2 hydrogens in either of this position. So the line broadening takes place and the signal disappears essentially, this particular case. Here carbon-nitrogen bond rotation is restricted because of the resonance structure, which gives a double bond character to the carbon-nitrogen bond. So these 2 methyl groups are exchangeable in position. At low temperature, they do not exchange. So they see 2 different methyl groups. At high temperature, a single methyl group will be obtained. 170 degrees centigrade, it's a single methyl group. Room temperature, 35 degrees centigrade, it's 2 different methyl groups are seen. With these examples, I hope I have been able to give you some information about dynamic processes studied by variable temperature NMR spectroscopy. a large number of interesting examples available in the literature. I picked randomly a few examples to show you how NMR is useful in studying some of these processes. If you have any questions, please feel free to ask me. It depends on what you are trying to study. If you are studying chemical rates of the reaction, where a starting material actually goes to a product, the spectrum due to the starting material and the spectrum due to the product sufficiently different, you will see both the spectra the same plot. Integration of the peaks gives you the concentration ratio of the starting material to the product at a given time. So with respect to time, if you follow the reaction using NMR spectrum, each trace will give you certain area under the peak, and that is proportional to the concentration that is present in the solution. Once you have the concentration of the product with respect to time, you can get the rate of the reaction. That is a way to study whether it is metal complex or otherwise. It's a way to study. The only problem you will have with the metal complex is if it is paramagnetic metal, NMR will not give you the information. At least one of these spin states should be diamagnetic in nature. Then you can use NMR. Both the spin states are paramagnetic in nature, then NMR will give a very broad spectrum which is not easy to interpret and integrate and so on. So it depends on the metal system that you are trying to study, whether it is paramagnetic or diamagnetic in nature. You must be all hungry now. There are no further questions. Let me thank you for your kind attention.